Welcome. We were talking about the ground segment, and in the ground segment we discussed different types of ground segment and their sizing based on the way they communicate and for the type of service they provide. And then we came to the different types of antennas that can be used in the ground segment, and in that last point we were discussing about the ITU regulation of ground segment, so that more number of satellites can be used. Let me draw the picture again. Let us have, this is the earth, let us say, and let us say this, there is a antenna here, and this is the geosynchronous arc. And if this antenna beam is this big, this much part of out of the total, we have 360-degree geosynchronous arc. Out of that, this much area this earth station is occupying. I should say you can have a satellite on which it is communicating. If I try to put one more satellite here, and if that is working in the same bandwidth, they will interfere to each other. Therefore, if I use a smaller beam, I can have a smaller parking slot. The word used is parking slot. So, there is certain ITU regulation that what should be the ground station antenna pattern, and they have provided a mask. You should not exceed that mask, so that you can have more satellite in 360-degree GEO arc. I should say arc, I am calling arc, it is actually GEO, full orbit 360 degree. Now, what is that regulation? It says that the gain of the antenna, that ground station antenna, in theta is angle from peak, that is bore side, should be 32 minus 25 log of theta for theta minimum. Theta should be between theta minimum and 48 degree, and g theta is equal to minus 10 for theta between 48 degree and 180 degree. Now this is true that theta minimum could be 1 degree for d by lambda of greater than 50, and theta mean is 2 degree for d by lambda of less than 50. Okay. So, when d by lambda is less than 50, that means diameter is smaller and beam is larger. So, theta minimum is 2 degree. Here itself you can understand why it is much larger. So, this is a mask given, and internationally all ground operators who are working on the satellite communication, they try to follow this mask, otherwise it will start interfering with others. And of course, there are side lobe specification, ITU mask for antenna side lobe. I think you remember what is side lobe. This is the main lobe and these are side lobes, smaller peaks. These are side lobes, and this is main lobe. So, ITU says that side lobes should be restricted such that 90% of side lobe peak should not exceed this relation g is 29 minus 25 log theta for theta equal to 1 degree to 20 degree, and for d by lambda of greater than 50 for larger station. Theta is angle from the bore side. This is theta. So, these are certain regulatory aspects for large station antennas. Now, there are different types of mounting the antenna, that is the parabolic reflector needs mounting, that means it has to hold the reflector. This is a reflector, so there has to be a, at the focus there has to be a microwave radiator which we call feed. It could be in the form of a horn or dipole, or generally horn is used. So, the mount has to hold the reflector, also it has to hold the feed. Feed cannot float in the sky, so feed has to be held. And of course, there is a waveguide or cable run. So, that is a waveguide. So, it has to make some arrangement for holding the waveguide or cable holding, and sometimes LNB or BUC will be mounted here. So, that is the holding for LNB and BUC, that is low noise block converter or block up converter, as we discussed earlier. So, therefore, this mounting arrangement and the radiation which is happening from the feed will interact, and let us see different types of mount that is used. I have some ready diagram for you. Let us say this is a prime focus mount. This one is called prime focus mount. Here the reflector is here, parabolic reflector, and at the focal point we have a feed horn, and feed horn has a radiation pattern like this. Some of the main beam of the radiation pattern is captured by the reflector, and then it is transmitting back. If it is ideal case, then it will go in parallel line, but in reality it will start forming. So, a beam will be like this. This is the secondary pattern. It may have some side lobes and all these things. Now, this primary pattern will have certain spillover, which is from the ground it will pick up noise, and full energy is not falling over this. So, shaping this is very important. Now, this type of reflector with a prime focus is very easy, very simple. You hold the parabola, and from the parabolic edge you put some studs, and there you mount the feed. Along with that you can put a block converter, block up converter, LNB, etc., and then run a cable along with this to your set top box or whatever, that is the baseband, IF and baseband unit. Now, one problem in this is that it picks up noise from the ground. So, G by T will be poor, and the second is there is a loss due to the waveguide run if you put the RF unit later, or if you put the RF units here, then it will give a larger blockage. Now, generally the antenna efficiency, this type of antenna is of the order of less than 60%, approximately people take less than 60% is the efficiency. Efficiency of this antenna is of the order of less than 60%, or sometimes 60% is taken. This is very commonly used thing, and in fact receive only you might have observed these things. You have seen the cable operator head end, from the building or from the rooftop, where the cable operators receive the satellite signal and then transmits through the cable, our TV cable operator. So, there you will see a lot of this prime focused and simple type of many antennas are there which are looking at different satellites, and then they are picking up the TV signals which are broadcast by those satellites and then multiplexing and sending through the cable. So, this is one of the common place where you can see this is very common, but then we have this blockage coming into picture. That is why people use another type of antenna which is called offset fed antenna. It is called offset fed mount. To reduce the blockage of the feed assembly, they use the offset fed mount. Means as if there is a total reflector is there, but only a small portion of the reflector material is used, rest of the things removed, and at the focal point the feed is turned towards the metal part of the reflector which is kept, rest of the things is not there. So, feed is not out of focus, it is not out of focus, it is offset. It was supposed to look in this direction, we moved it a little, so it is offset. The advantage is in this path where the main beam of the reflector is coming out, secondary beam, the feed is not coming in that, and along with that feed, if you use the BUC or LNB, that blockage is not happening here. So, to reduce this blockage of feed assembly, this type of offset fed antenna is used. Is of the order of 60% efficiency you get, but it is most popular as a VSAT mount. You can, as I always see that always tell you that you can go and see near the bank ATMs, many of the bank ATMs they have this VSAT antenna, and it is a offset fed mount. You will find that from the feed assembly you will find two cables are coming out, one for the uplink, one for the downlink. So, it is very interesting. You should always look at how people really use the satellite communication terminals. So, this antenna is the most visible part of it, since large antennas are there. These are of the order of 1 meter to 1.5 meter, sometimes 2 meter, 2.5 meter antennas are also there. So, this is another type. For much larger antenna and where you need to improve the efficiency, this Cassegrain mount is used. Cassegrain mount you can see, and trying to draw, this is the reflector, and then the primary feed horn is a hole made at the center of the reflector, and it is there. So, how do I reach the focus? From here the radiation takes place, and then there is a secondary parabolic subreflector is there. So, from here the energy goes up for radiating out from feed, it goes up, gets from the subreflector, it gets reflected, comes to the primary reflector, and from the reflector it goes out. So, this is the path, this is the path it takes, and its beam is like this. Now, one big advantage on this is that you can mount your LNB, HPA, LNA, all these things behind the reflector, and since the secondary reflector as well as the primary feed both are looking towards the sky, the ground noise pickup is less. From the ground noise, it is not falling into the beam of this as well as not in this beam. So, the ground noise level is less, so G by T can be controlled. And of course, there is a very small waveguide line because you can mount. One difficulty is there. There is one difficulty, that is, in case by chance if these antenna has to be moved to another satellite to look at the another satellite, or it has to track some satellite, your azimuth and elevation has to be moved. You have to move azimuth and elevation, and then fixed waveguide will not work. In that case, you have to use a flexible waveguide along with that, and flexible waveguide will introduce some loss. So, this is one of the drawback in this system, but generally these are used for larger station and its efficiency is 70% or sometimes larger than that. This is for 9 meter, 10 meter antenna, the Cassegrain reflector, or larger is greater than 10 meter antenna, in general I can say use the Cassegrain mounting of the antenna. But then this turning of elevation and azimuth, since that create a problem, you make a 360 degree or 180 degree turn, and then all this waveguide will get fully twisted, it creates a problem. So therefore people have come with a innovative solution. One of the solution is like this, that is for very large station they use beam waveguide antenna. I am trying to sketch it. That is, this is the parabolic reflector, and this is the secondary hyperbolic reflector, and my feed horn is here, and there are small reflectors, flat reflectors are there. So the power goes from here, gets reflected from here to there, and then this goes to another pair of small sub reflectors, goes like this, and then it goes out through this hole at the center of the primary reflector, goes to the secondary reflector, and like this it goes out. So our final beam is like this. Now the advantage is, since there is no waveguide here, you can turn the azimuth elevation axis like this. So the antenna will go up and down like this, and azimuth can be on this axis, you move. So this set of two pairs of reflectors, this combination avoids us of having a flexible waveguide, which is a lossy waveguide. So this is a very big advantage, and on very large station in some of the cases people use beam waveguide antenna. So like that there are many innovations on the antenna. I try to give you a glimpse of this antenna system. Now one of the basic issues, let us go back, this is that we said that there are VSATs. VSAT is called it's called very small aperture terminal. Of course this word very small came in the year 1980s, I should say. Earlier than that, in satellite communication people were using the antenna of the size of the order of 7 meter, 9 meter. The smallest one was of the order of 4.5 meter or so. So when people started talking about a 1 meter antenna, 1.5 meter antenna, obviously it was called very small aperture. Our antenna aperture is much smaller, the diameter of the antenna is very small. Now it has big advantage. The advantage is it is easily handleable. You can mount it on a rooftop, it does not have much weight, you can mount it on a lawn. So why not a VSAT can communicate with another VSAT? I mean, it has been seen that VSATs are not communicating directly with another VSAT. Let us see. That is VSAT always need a large station at other end. A large station is required at the other end. It means why that there has to be a large station, or it is, which is hub, we call it. The term hub will see why it is called hub, but why there has to be a larger station. Now to understand this, let us do some small calculation. I think for this part I will give you some familiarity of doing the calculation what we have done in our C by N calculation earlier. You will go through a quick calculation and try to see how much power is required, how much power amplifier ratings are required for a VSAT. if a VSAT has to directly communicate with another VSAT. You should keep your calculator ready, and I will try to show you some calculations. You must verify these calculations and do it yourself. Okay. So, let us start with some assumptions of numbers. Assume that same small antenna, that is for the VSAT, is at both end, that is VSAT to VSAT communication directly via satellite, of course, and we will estimate the power amplifier requirement. Let us assume some numbers. VSAT antenna dia for both sides. Let us take easy numbers, 1 meter. Then frequency, that let us call receive frequency, is 12 gigahertz from the satellite, and the antenna efficiency is 60%. Receiver noise figure is 1 dB. Sky noise or antenna noise is 25 K. The transmit frequency, that is from earth to satellite, is 14 gigahertz higher. For the timing, we will keep the transmit and receive both antenna efficiency same, and then there is a transmit feeder loss of 1 dB. Let us say the bit rate of transmission is 8 Mbps transmission with EB by N0 of, with error correction, it is 5 dB, that is with error correction for a particular BER. Range from VSAT to satellite and back is 40,000 kilometer, both for the transmit side and the receive side. That is, one VSAT is communicating with another VSAT. For both sides, it is roughly about 40,000 kilometer. And miscellaneous loss, which may be due to depointing, due to atmosphere, many other losses that may come, is loss is 2 dB in both up and downlink. And for easy calculation, we will take transponder or we should say satellite, I mean including the antenna, everything, transponder block gain is, let us take the number 166 dB. This, when I say transponder gain, it is as if the block, the satellite block is gain is 166 dB. That includes the gain of the satellite antennas also. Okay. So, with this number, if we try to calculate what is the power requirement from the, find transmit power from VSAT, transmit power amplifier output, let us say. Okay. Let us do this calculation slowly. Now, let us say receive antenna gain, you have to calculate G by T. So, for that receive antenna gain we will call GR is efficiency time pi diameter of the antenna, lambda is written F by C whole square, and if you put 0.6 here, D is 1 meter, this is received, so it is 12 gigahertz, F, C is the velocity of light or electromagnetic wave in this case, 30 10 to the power 8 you can take, and with this remember all the this was given in kilometer, sorry this is in sorry it is not loss, sorry this is in meter. So, this if you calculate it will come to about approximately 39.8 dB. Similarly, you can calculate the transmit antenna gain, which is GT. Similar thing, only the frequency changes. This is frequency received and this frequency transmit. Eta is same, diameter is same. So, only the frequency changes, you will find a number like 41 dB. And if you calculate the transmit sorry receive system noise temperature, which is the sky noise or antenna noise plus 290, that is f minus 1, f should be, I should say NF noise figure in ratio. So, 1 dB has to be converted, you will get 1.26 in ratio, f is equal to 1 dB if you remember. So, Ts will come out to be 25 plus 290, 1.26 minus 1, which is about 100 K, which is 20 dBk. So, G by T is receive antenna gain 39.8 minus 20 is coming out to be 19.8 dB dB per Kelvin. Since time is going up, so we will continue this discussion in the next period. For the timing, thank you very much, but do this calculation with your calculator. We will continue with it.